The topic of this lecture is on ignition and extinction. Actually, I will start with extinction and then talk about ignition. It's not the inclusive discussion of ignition and extinction, but selective aspect of them. So the first thing is just a minute. Let me just make sure that, okay. I said I change a pointer, so I have to get used to the. So the first one is an example of flame extinction by heat losses. And so we, again, are going to consider the setup of the simple planar flame that we discussed yesterday, again in a coordinate system which is attached to the flame. So in a coordinate system attached to the flame, far to the left you have the unburned gas, which is at a given temperature, Tu, density rho u, mass fraction Yu. Sorry, and the incoming velocity towards the flame is some speed s. It is not the laminar flame speed because due to heat loss, the velocity will change. But to hold the flame stationary, then the incoming velocity had to be equal to that unknown speed s. And far to the right, you have the burn gas that expand and goes to a uniform state. So the intention or the plan is to add heat losses, and we are going to add a volumetric heat losses, which means that it's a loss from the entire volume, not from walls or anything like this, even though I'll show you an example of heat loss from the walls later on. So due to heat losses, the speed will be lower than the laminar flame speed, and we want to address this problem. Again, we are using only a single reactant, so let's say lean, the fuel, and the governing equation are going to be the continuity or conservation of mass. Rho u is a constant, so it gets pulled out here, and you have the energy equation and the species equation. Species equation with the rate of consumption of the reactant. By the way, I didn't say that explicitly, but I think it's obvious to all of you who have been working on combustion that always in the species equation, that term is negative because it's consumed, and in the energy equation it's positive because it's produced heat. So this is the heat release, and minus, because it's loss, G of T is going to be the volumetric heat loss. And G of T can be, for example, like some constant K, a difference between T and the unburned temperature or the ambient temperature Tu. It's a conductive loss. Or if you want, it can be radiative loss T to the 4 with K related to the Stefan number and the more radiative aspect of the problem. So this is, and in fact, you're going to see we're not going to specify the functional dependence G in the discussion until the end. Okay, so in other words, it's going to be for any general G that you like. But it's volumetric because it enters not in a particular place, but throughout the whole volume. So the equation need to be non-dimensionalized, and the details are written here. The idea is that you use the laminar flame speed to non-dimensionalize the speed s. So the little s here is the scaled flame speed, which clearly is going to be less than 1. And the flame speed is laminar flame speed expression for this condition that we derived yesterday is written here. It's put in because then when you reduce all the parameter, in particular the dam color number in omega, it depends on SL. I didn't write here omega explicitly, but anyway, it should be there. Little q is the heat release like before. TA is the adiabatic temperature, which here it's in dimensional form, here in dimensionless form, and everything else is almost clear from the notation. Oh, two things. TF is going to be the flame temperature, which may not or will not be the adiabatic temperature, clearly. And the heat loss term was scaled as such, and I'll say a word about it in a minute. Here, the TA minus 1 was just put in for convenience. It has not just renamed G, if you like. But the important thing is that there's a 1 over beta in front of it, and beta is a large parameter, is the Zeldovich number, or the large activation energy parameter. And so basically, what we are assuming a priori is that the heat loss are small, are weak, not very strong. Well, you can ask me from the video, so what's the reason for making an assumption? Maybe, well, if I show you through the analysis that a weak heat loss can extinguish the flame, then a strong heat loss, of course, will. So really, it's a reasonable assumption for now, unless it's proven otherwise, right? This is always true about approximation assumption. You make an assumption, you test it by the result. And how do you test it? There is no theorem, there is no any other mathematical way to determine if your assumption is right or wrong. When we talk about asymptotic or perturbation, we have a small parameter. Mathematically, it's true that the approximation becomes more and more correct when the parameter goes to 0. But it doesn't tell you ever that the approximation is good if it's 0.01 or 0.1 or 1 or 3. So there is no. So what is the test? The test is that if it produces physical picture which is commensurate with the experiment and can be at least approximately describe the experimental observation. Or I use the word experiment, but experiment can be numerical simulation as well. It's not clear which comes first. Sometimes this before that, sometimes that before this, but this is how the jury is, if it's correct or not, or it's good or not. So, so we have the continuity, the question for y, the temperature equation, and we have to deal with these. And the boundary condition here, I think, are clear and obvious. I discussed them. I just remember that when I went through this lecture, I modified the description of what you have in the notes. It's not to say that what you have in the notes is wrong, it's just I think I put them in a way that they can be better presented. So it's a matter of choice. So anyway, I mentioned that so that the first thing is that, again, we can add the temperature and species equation to eliminate the reaction term, but still we have the heat loss term to get this expression. It's an expression that it's important to remember because I'm going to use it later to integrate through the flame and get some information from it. For the large activation energy assumption, the reaction rate, as we did yesterday, reaction rate is 0 on either side of the flame. Remember, now I should correct the word I just said, on either side of the reaction zone. Now it's not a hydrodynamic model. We have scaled things on the diffusion length. So we have a thin reaction zone, we have a preheat zone, which is significant. On either side, so these are effectively the equation that we need to solve. This is just a reminder from yesterday that we can generalize the analysis of the reaction zone by saying that effectively it's equivalent to saying that the concentration and temperature are continuous across the reaction zone, that there's a relation between the gradient of the temperature away from the flame, or the jump in the gradient, because with heat loss you also have temperature gradient on both sides, and the concentration gradients, and that and this is this relation, the flux of reactant, the mass flux of reactant entering the reaction zone is proportional to the difference in the temperature between the adiabatic and the flame temperature when the two are different. I again repeat that this was hand-waving generalized, but it was derived systematically in appropriate paper. So when I take this relation and I express it in dimensionless form, I have here a Lewis number that effectively comes from this rho d and some other adjustment of the coefficient. And on the right-hand side, the difference here between E over TA and E over TF, since the assumption will be that small heat release will cause a small change in flame temperature, then the flame temperature is written at the adiabatic temperature plus a small change. Again, the TA minus 1 is only for convenience. The small change is phi star, the unknown. And when you plug it in here, in this expression, the exponential become e to the minus phi star over 2. When I say for convenience, is so that in the exponent I don't have that additional factor, that's all. So I renamed phi star to be what it is. Okay, so when I now put in that recollection from yesterday into my model, these are the equations I have to solve subject to this jump condition across the reaction zone. Note that phi star is not known, is one of the unknown, and little s, which is also another unknown, flame temperature and flame speed, okay? Or accurately, more accurately, deviation of flame temperature from adiabatic, deviation of flame speed or fractional flame speed from the laminar flame speed, okay? Those are the two unknowns in this mathematical model. Other than that, this is a complete, consistent mathematical model that need to be solved. So we first solve for the species equation. It's easy to solve in the unburned gas. It's an exponential like this, and then the burned gas is 0. And we can compute the mass flux that was in that jump relation, right? So the derivative here gives you the S, and so you get S equal e to the minus phi star over 2, which is a relation between the flame speed and the flame temperature, okay? This slide is a little different than what you have, but you have it there somewhere. And then you go to solve for the temperature, and for the temperature in the unburned gas, it's quite easy, because the heat loss is small, so it's 1 plus TA minus 1 e to the Sx is simply the solution of this equal to 0, plus perturbation, but I didn't write it because at the moment it's not important. What about on the burn side? On the burn side, we said that the temperature is expressed this way, that was Tf, right? And so we write T as the flame temperature plus a small perturbation from the flame temperature. And we need to compute that T1. Why do we need to compute that T1? Because one of those jump relations before here include the jump in the temperature, okay? And that require going to that order to determine the jump in, or at least the gradient in the burn side. So, so here we go to T1. When we substitute For T1, of course, now we get the heat loss term appearing on the right-hand side. But since the leading order is TA, it's relatively easy to compute. This is just the value of the function g evaluated at TA. And when you integrate this equation, the exponential solution is not acceptable because it blows up at infinity. So the coefficient in front of it is 0. And you get only a particular solution from the right-hand side, which is just proportional to x. So now we have the temperature with the two unknown, phi star and s, related that way. Okay? So the next step is to determine those. I think before doing this, I just put a plot here to show you what we have accomplished. Here is the y, the mass fraction just drop to 0, stay at 0. The temperature, of course, the scale of those two graphs is not the same because this is 0 for y, this is 1 for t. T goes from 1 up to the adiabatic temperature. Under adiabatic condition, it will stay T equal to TA. Due to the heat loss, you have a linear decrease here of order beta minus 1. Okay? A question about this I will raise and discuss later, but let's proceed for now. So we want to evaluate the flame speed and the flame temperature. We go back to that relation that I mentioned earlier, which is obtained by combining T and Y equation and eliminating the reaction term. And we integrated from, oops, I did something wrong. Did I do? Sorry about that. And so what I do, I integrate the equation from negative infinity all the way to 0 plus, meaning up to and beyond the reaction zone. Why doing this? Is just because I would be able to extract the information that I need. If I integrated up to 0 minus, I get things that I already know. So there's no trick here. It's just that's what you determine need to be done. So when you do that, you can evaluate, the proper terms. What you see is that the difference TF minus TA is of order beta minus 1 and can be computed from the previous slide to be essentially phi star. This derivative can be also computed. Remember, it was a linear decrease in the burn side, so the slope is just that, and it's beta minus 1. And the right-hand side, it's a quantity of beta minus 1 that involves the heat loss. So we have three terms, all of them beta minus 1, beta minus 1, beta minus 1, factor out, canceled, so it's of the same order. And this is the mathematical equation that result, okay? This is one equation with the two unknowns, the second equation with those two unknowns. Of course, the second one can be expressed in terms of phi star, which is what I do in the next slide. So S equal to that tells you phi star is minus the log of S squared. By the way, in one of your notes, there may be a minus missing somewhere, but you can easily determine that if you verify the algebra. And then if you substitute in the other one, you replace the phi star, you get a single equation for S of this form. Now remember, this is G of T, of the temperature. And so the integral is from negative infinity to 0 plus, which is the same as 0 because the function T is continuous. And so essentially it's in the unburned gas. So this is G of this quantity. So it's an integral that what you want to do, you want to change the variable. Instead of G of T, you call that Z. And so it's G of Z, and then you do the change of variables. So dx is going to be related to dz and turn out to be dz divided by z minus 1. So anyway, and there is an s that appears from here. You multiply on the left-hand side. Anyway, the end of the story is that you have this turn out to be s squared log s squared, and here you get minus that integral plus g of ta, which I combine together. It's a definitive integral, so it's a known number. Knowing the functional form of the heat loss, you can compute. What does it represent physically? Well, this is essentially the total heat loss from 1 to Ta, or from negative infinity to 0 on the x scale, which is the unburned gas. So that's the total amount of heat loss from the unburned gas. And G at Ta is approximately the leading temperature on the burned gas, so that's the heat loss from the burn side of the gas, and so that's the total heat loss. And it's negative x. And what it remains is to plot, to graph this function. And before doing that, I just said here that for a conductive loss, say when g of t is kt minus 1, then it's easy to integrate this. You get that it's 2k ta minus 1 expression. If it's t to the 4, you can integrate it numerically and you get a number. The idea is that QL is known. Okay, so now you graph it, and that's what you get. It's easy to see that when there is no losses, there are two solutions on the left side. One of them is S equal to 0. The other one log S equal to 0, which is S equal to 1. So those are this one and this one. And then this function just has a turning point, and you can compute it easily by taking the derivative. Of course, if you want to do that easily, you just think of turning yourself around, and instead of looking in other words, the maximum of the function when it's a function of s rather than x, but it's a detail. So what you get is there is a turning point here, and the understanding of this curve under the assumption that the lower part is unstable, both phenomenologically it is such because you add heat loss, you increase the speed is not physically realistic, but also you can verify it mathematically that it is unstable. Then the idea is that if you start, let's say, with an adiabatic flame, you increase the loss, then the speed is lower. You increase the loss further, you increase QL, then the speed is smaller and smaller and smaller and smaller up to this point. You get to this point, you increase the speed, you increase the heat loss, there is no solution. In other words, there cannot be a flame that propagates under no speed with this amount of loss, and it is interpreted as a total extinction. And the QL critical is approximately 0.37 in, of course, dimensionless. But what is something to more remember, which is interesting, is that the flame speed at extinction is about 0.6 from the laminar flame speed. In other words, you reduce the speed to about 60% of the laminar flame speed, the flame will extinguish. So before we continue, the first question that I wanted to pose before, when I say I'm going to delay it, it is just to be maybe a bit more precise, if you like. The first question is the burn gas decrease linearly, but if it decreases linearly, I mean, it goes to negative infinity on the right, it makes no sense. So how do you interpret that? Okay, you cannot just say, okay, that's how the solution is. It's not. It has to have some physical meaning. It had to have some consistency. The idea is that on the burn side, there is the loss or the heat loss causes the temperature to decrease, but on a much, much larger scale than on the scale of the flame thickness. and the scale, the appropriate scale, turned out to be beta times capital X. And so when you rescale that in terms of capital X, you get that capital X is given by this. This is the solution implicitly, or for conductive losses, it's simply an exponential, but an exponential that decay much, much slower than before. And so the clear picture is that there is an exponential decay to zero, which is physically more realistic, and that on the always do that. And on the, actually I did something right. And on the, on the diffusion scale, then it's nearly linear, as you see here, okay? So it gives a complete picture of the problem. The safety lamp devised in the 1800 by Humphrey Davy to use in coal mines is based on this idea that they put a metal goes on the around the lamp where the flame is, at least dense enough so that there is sufficient heat loss that can extinguish the flame. Extinguish meaning it doesn't propagate out in this case. And it can be used without avoiding explosion. The next one, the next example is if you have heat losses in a tube. Remember that the heat losses that we have been talking about is per unit volume. It's a volumetric heat loss. So the total heat loss from the wall, it's going to be the length times the circumference. And the heat loss QL per the volume, if you divide by the volume, you get QL is 1 over R, which means that QL is sufficiently large to extinguish the flame is equivalent of R being sufficiently small for the flame not to propagate in. And this is how experimentally you determine flammability limit. You put a torch, you let the flame propagate through the channel, and if it does, great, you reduce it until it doesn't, and you say that's the radius. By the way, note that in the discussion earlier, I made a quote-unquote weird assumption that the width is comparable to the flame thickness, which may suggest, oh, the flame will never propagate. But really, we did not do a discussion with heat losses. So in the absence of heat loss, it will propagate no matter what the radius is, at least in principle, right? So anyway, this is that. Here is some computation that were done long ago, but under the assumption of constant density. In other words, we just didn't really account for gas expansion and the changes in the velocity of the gas. And the idea is that you have a channel and you have heat losses at the walls. Apparently, when I touch it too long, it switched to that, I don't know. So you have the flame is propagating in between the two channels, and there are some heat losses. Note that the flame is not necessarily flat, and we're going to see that soon due to the there is variation in the y direction as a result of these losses, okay? And so this is more or less the setup of the problem. An important parameter I'll show you in a minute is delta, which is the ratio of A to the flame thickness. In other words, it's a measure of the flame of the channel width, okay, in terms of, I'm not saying it's small, I'm just saying that that's what that delta is. Now, the heat loss at the wall is assumed to be conductive, so it's not volumetric heat loss from the walls, and the heat loss is just the difference in the temperature between the local temperature and TU, okay? So there's heat conduction out or heat loss out. When K is equal to 0, dt dy equal to 0, which means adiabatic condition, no losses. The extreme other limit is K going to infinity, which means K times dt dy is 0, so T is TU, which means isothermal condition. So in principle, K can vary from 0 to infinity, covering all these different conditions. What did I say here? Result was assuming beta 10, which is approximately a good number for hydrocarbon, and unity Lewis number. Lewis number have interesting effect in such a problem, but I will not discuss it now. Maybe I'll make a comment without notes later. So here are some of the results that you see for a delta equal to 20, which I refer to as a relatively wide channel for reason that you will see in a minute. K equal to 0, remember, is a adiabatic condition. So you expect the flame to be flat. The flame is flat. What you see here are reaction rate contour. In other words, it's a computation, it doesn't assume anything about the rate is a finite rate, so different omegas, right? Different value of omega, it gives you a picture of different reaction rates and therefore more or less the shape of the flame or the reaction zone. And these are temperature isotherms. So you see a constant line because flat flame. Okay, you increase K, you have more heat loss, the flames start to curve, and that's what you see here. You can go all the way to K infinity, well, a large number, numerically, not infinite. And what you see is that there is a dead space here, which means the flame, or there is no reaction in this region, the flame doesn't reach all the wall, but it exists in the center of the channel, no matter what the losses are, okay? Now we go to a narrow channel, delta equal to 13 as opposed to 20. Again, for K equal to 0, the flame is flat. You increase the loss, it's a little different than before. It's more or less, it's curved, a little more curved and spreads wider. But you reach a point, 28.1, and you get this flame at the center. If you put 28.2, or I don't know, maybe 28.4, you cannot get any solution, no solution, okay? So again, it's interpreted as at that point you have a total extinction for K beyond some critical value. And now here is the picture of the propagation speed as a function of that heat loss, the K parameter that I showed you before. Delta equal 1, 2, 4 is very narrow channels, right? What's interesting is that the speed decreases. That's like the S curve that we saw before analytically. And the extinction occurred at approximately 0.6, like theoretically was observed before. But when the channel is become wider, then the flame speed decrease, but it keep on decreasing and there is no total extinction. In other words, there is condition where you have total extinction in narrow channels, but only partial extinction otherwise, and the quenching distance associated with total extinction appear to be in the range of what is experimentally observed. The quenching distance, as I described before, is the minimum distance between two plates that a flame can pass through. And then you have partial extinction in those cases. And here you can measure the dead space that I showed you in the picture before, and experimentally dead space are of that same order. Again, those were long time computation. Today, I'm sure it can be done more accurately and with more details and better comparison. But the idea is there. Another interesting example is to the flame in a straining field that I discussed yesterday. We have seen that we can compute the velocity field and so on. And yesterday we assumed that the flame speed, well, I did one case that the flame speed is just the laminar flame speed, even though in the literature you could have seen also when effect of stretch are accounted for. But here I'm going to use a model for the flame speed, which has been referred to in the literature as slowly varying flame. The reason it didn't really catch up beyond when it was derived in the 80s, it's because it turned out that it leads always to unstable flame. In other words, there's some pathological instability in this model that hasn't been really, cannot be used for more complex situation. But for planar flame, it works well. In fact, many experimentalists like to say, oh, we can, I don't like to criticize, and it's not a criticism, but it's an important comment. Usually, when you have a lot of data, you try to fit it to some analytical form or analytical formula or analytical theoretical derivation. And so when things don't fit for them well with the flame speed, flame stretch relation that we discussed yesterday, which is linear, and they say, oh, but our data is a bit more linear, they try to fit it to something like this. To be honest with you, it's not totally, there's no much meat in it, because they do that in order to extrapolate the data to zero stretch and determine the flame speed at zero stretch, which is the laminar flame speed. So the intention is correct. But really, when you extrapolate this formula, or you extrapolate, or you take the other formula, they are both linear when you approach zero stretch. It's just, it looks SF square log SF, but for small stretch, it's linear. So, okay, so you like this, fit it to this. But, it's an important observation to emphasize that it's the same thing. Anyway, when we use this formula, which is very similar, by the way, to the one that you have seen with the heat loss analysis that we did, there is a parameter, gamma, here, which is nothing more than related to the deviation of the Lewis number from 1. So there is nothing special. It's a parameter that it's like a Markstein length, if you like, but no, it comes from this analysis. In fact, gamma is positive for Lewis number bigger than 1 and negative for Lewis number less than 1. It's a definite integral, can be evaluated. Probably I have a graph of it. What's more interesting is this relation that is related to the strain rate here, epsilon. And what you see, by the way, this is the gamma, this value for Lewis number bigger than 1, negative. So anyway, it's a number. But of course, it's important to remember it's positive and negative depending on above 1 and below 1 Lewis. So here is the graph that you get. Again, it's a curve that has a turning point. No turning point for when when gamma is negative, in other words, for Lewis number less than 1, but there is a turning point when gamma is positive, which means that there is total extinction here. In other words, the flame speed due to the straining keep on decreasing when you increase the Lewis number up to a certain point and the flame is extinguished. This is better interpreted in terms of the flame location, and here is the graph from the flame location. So this is what's interesting about this problem. Remember, now it's plotted versus the strain rate. The strain rate is the velocity gradient that the reactant is coming towards the stagnation point region. Now, if the Lewis number is very small, like 0.75 gamma negative, the flame, you push it harder, you increase the strain rate, flame get closer and closer and closer to the wall, okay? And it will reach the wall when, strain rate is very high. When it gets close to the wall, of course, the question is the interaction with the wall, so it's not described in this model. There may be other things that are happening. But what happens when the Lewis number is sufficiently large? You increase the strain rate, flame come close to the wall, and at a finite distance from the wall, it gets extinguished. And this has been observed experimentally. In fact, this is, I think, I'm not 100% sure, but probably correct, that this was described by Sivashinsky at the first time. I think it's one of the examples that the theory have told you the answer before experimentally it was observed, okay? And it's not surprising that there are such things exist. Okay. I wanted to say a few things about ignition, but I will be brief. I'll let you see the rest in the notes. So ignition is related to explosion because if you have a small amount of combustible material exploding, it's like it ignites. I mean, in a big sense, it's explosion. In a small scale, it's an ignition. Okay, so they are both related. And one of the simplest theories due to Semenov, first of all, under adiabatic conditions, so essentially you have the temperature rises due to the chemistry and the mass is consumed. There is no motion, it's assumed, it's a homogeneous combustible mixture in a vessel, say, or in a region, in a volume. And so you see, you can again add the equation to eliminate the reaction term, and you end up with the adiabatic temperature, which is different than the adiabatic temperature that we have been talking about until now, because you see in a closed vessel, it's not under constant pressure, and adiabatic flame temperature was defined under isobaric condition. The difference will be that instead of a Cp here, you're going to CV, and since Cp is always greater than Cv, or Cv is always smaller than Cp, then this is always larger than the adiabatic temperature. So this is the adiabatic temperature in constant volume. Okay, so this is one thing. And then because of that relation, there is only one equation for the temperature. It's a simple ODE, but nonlinear. And despite that, if you integrate it from, let's say, initial condition, T at 0 is 1. And despite the fact that it's very simple, mathematically it's a very complex form. It's an exponential integral that appears on the right-hand side. The solution is implicit. Okay, you can graph it, but it's not very illuminating. Anyway, if you do that or you integrate the equation numerically, you get a curve that goes from 1 all the way to the adiabatic temperature when all the material is consumed after some time. And when you increase the activation energy parameter, you suddenly see that change occurs more rapidly at some location. So you see, if I want to define ignition, I don't know how to define it in this case. It's going to be a bit, determination, where do you call ignition? Whereas in that large, when beta naught is large, which is typically true in combustion system, it is more when this rapid change occurs. So again, it's in some sense some asymptotic concept. Okay, that's my point. Ignition is an asymptotic concept. And so how can we describe T ignition? What we are going to do is say that the temperature in the early time changes slowly from 1 until we capture that rapid change, okay? That's where ignition occurs, and then later, if you are interested, you integrate the rest. And so here is the small variation, the perturbation from 1, and you see that you obtain an expression that T goes like log 1 minus QT. So when T is 1 over Q, then the log goes to infinity, and the temperature goes to infinity, and that's, of course, it goes to infinity as a perturbation from 1, and so then there is the rest of the curve. But I'm interested in defining ignition, and so I have a very clear definition in terms of physical quantities, okay? So the question is, if you have a vessel of a certain size, you know the mixture, you know, when would it explode? When would the ignition occur? So that gives you at least a first order idea. And you can then incorporate the heat losses to the system and extend that discussion. And now the parameter, the crucial parameter, is going to be a combination or a product of the heat release parameter and the heat loss, which is conductive loss divided by, or conductive time divided by reaction time. And what you get now is, well, now that you have heat loss, the question is this. Well, so there is a reaction start to occur, temperature rises. Well, if it gets dissipated enough at the walls that get lost, you will reach a steady state. If it doesn't, then it will explode. And so that's what you want or you're interested to find. And so this is the condition for steady state, where we assume dt by dt is 0, in other words, no change in time, so you get steady state. The exponential is the red curve. The linear function here is one of those. So when it's, and it depends on this parameter d, which is a Dam-Kohler number or something related to the heat loss that it was in the previous slide. So when they intersect, there is a steady state, which is here. When it's tangent, it means it's just a critical condition. And when the slope is a little less than that, then you never have any ignition, then you have an explosion. And so this was led to, and you can, this is what the temperature would look like if you reach a steady state or not. Very often this is called thermal runaway. In other words, the temperature run to infinity, or mathematicians call it blow up at a finite time. An equation, you know, the heat equation, for example, does not have such a behavior, but sometimes a heat equation with additional nonlinear effect may blow up at a finite time, and that's such behavior. So anyway, this is some of the details where you can obtain an explicit criteria for extinction. Note that it depends now on the surface of the vessel, the volume, the reaction terms, and so on. And for example, you can interpret that as a critical pressure, or you can interpret it as a critical vessel size, as you wish. So there is a critical pressure below which there is a slow reaction, above which you have explosion. And the last of this series is the Frank-Kamenetsky theory that now allow also for spatial variation, right? Heat conduction. So before we have assumed that it's a homogeneous. Semenoff theory is homogeneous system. And so again, you put it in dimensionless form, and you have this delta similar to the coefficient before. It's often referred to as the Frank-Kamenetsky parameter. And T at the wall is equal to the ambient temperature, which is 1. So now it's not the volumetric or heat loss from the wall, it's throughout. And the question is, again, the same philosophy as before. Are there any steady states? So you take dt by dt out, and so you want to solve the problem that the Laplacian equal to the reaction. So when there is a balance, it means a steady state will exist. When there is none, it means the explosion would occur. So that gives you the critical delta. If you perturb the temperature from the initial condition 1, you get an equation of the sort. It's known as the Frank-Kamenetsky equation. It's an interesting equation. It can be solved analytically in one dimension. You see the Laplacian takes the following form: n equal to 0 for planar, n equal to 1 for cylindrical, n equal to 2 for spherical. Actually, it can be solved analytically for 0 and 1, in other words, for planar and cylindrical, but for a sphere, you have to do it numerically, but those are the curves that gives you the critical condition and the turning point. This is for planar, cylinder. It's interesting that for cylinder, it's a very tricky way to solve the equation when it gives you a delta equal to 2. But anyway, that's a curiosity, nothing more. And this is for spherical. And it was discussed by Harris long ago in his book. I don't know if you know, if you guys know these names. Harris is a well-known chemical engineer, and they were interested in this type of problems. He has a couple of books in this area. And anyway, so really this is the last thing of my notes. I added something here about, if you also account for some losses at the wall or not, but I'll let you look at that by yourself. And this is the end of this discussion.